Hello everyone, my name is Prerak Pandari and I'll be presenting the algorithm to create the Burrows-Wheeler transform of the reverse string. So I'll begin the presentation with an understanding of some basic terminologies used and then some understand the problem statement. After that, we'll move to the main algorithm. Post that, I'll explain the algorithm in detail with a step-by-step iteration using an example. Once we understand the algorithm, we can see its recursion tree representation and then see the proof for its worst case time complexity. Finally, we'll come across some practical usage of this algorithm. So here are some concepts that I'll give a brief about, but would recommend having a good understanding of before diving into the actual algorithm. The first is Burrows-Wheeler Transform, which we also call it as BWT, and then we have wavelet trees, then we have string and the reverse string, and finally the suffix array. The BWT of a string can be computed easily by sorting all of the suffixes of S. Hence, suffix array SA of the string is already known. The Burrows-Wheeler transform is an algorithm used to prepare data for use with data compression techniques such as bzip2. It was invented by Michael Burrows and David Wheeler in 1994. The algorithm can be implemented efficiently using a suffix array, thus we can achieve it in a linear time complexity. It has various applications such as it is used for sequence alignment, for image compression, for compression of genomic databases, and for sequence prediction. And there are many more other use cases of BWT. We can calculate the BWT using the formula shown here on the slide, which is T of SA of I minus 1 if SA of I is greater than 1 and dollar in any other cases. A wavelet tree is a data structure that recursively partitions a stream into two parts until we are left with homogeneous data. Wavelet tree can be used to answer range queries efficiently. So a wavelet tree converts a string into a balanced binary tree. As you can see over here in the image, I have a array of elements from 1 to 8 and the elements can be repeated. Now in a general tree we sort or we take the index values of all of the arrays, but in wavelet trees we take consider the element or the value of that particular index. In this case we have elements from 1 to 8 which are at our root node. So the root node considers all of the elements and we'll be using the same concept later on to generate the BWT reverse of the string. So since we have the elements 1 to 8 at our root node, we split them in half. So the left node will have 1 to 4 and the right node will have 5 to 8 elements. Now all of the elements that come under this range of 1 to 4 will be taken into the left part of it. So we have 3, 1, 2, 4, 1, 2, and on the right part of the tree we have 7, 5, 6, and 8. Similarly, we keep on dividing the tree until we are left with single elements at the leaf node. Now string and the reverse of the string. So if we reverse the order of all the characters in a given string, we can achieve the reverse of the string. Now in a given string, we have a delimiter of dollar at the end of the string to determine that the string has been terminated. But in case of a reverse string, we do not consider the dollar symbol at the start of the string. We simply ignore the dollar symbol and then reverse all of the characters of the string and append the dollar symbol at the end of the string again to obtain the reverse string. So for example, if the string is CT dollar, the reverse of the string would be GT and then dollar. Now, a suffix array is a data structure that stores all of the suffixes of a string in a sorted order. For the examples shown, once we write all of the suffixes of the given string and sort them, considering dollar to have the lowest in the order, we can get the suffix array by noting the starting index of the suffixes. And BWT of the same can be calculated using the previously shown formula. So as we now know that one can find a BWT of a string given the string and its suffix array, but since there is a strong relationship between a string and its reverse, can we also find the BWT of the reverse string without actually reversing the string? So that's the problem. So if you just have the string and you cannot reverse the entire string to calculate the BWT of it, how do you calculate the BWT? So yes, this indeed can be solved, and the worst case time complexity for this is order of n log sigma, where sigma is the length of the alphabet set. The same algorithm can also compute the suffix array reverse and the LCP reverse, which is the suffix array and the LCP of the reverse of the string, but only partially. So there are some modifications which we can do to the algorithm that can complete these arrays as well. So here is the main algorithm used for computing the BWT reverse array, which is essentially the BWT of the reverse string. The algorithm recursively computes the BWT reverse of the string by procedure call, making a procedure call to BWT reverse. Here we take three parameters. The first is k, which is current position in BWT reverse that we are calculating. Second is a range of I to j, which is interval of suffix array of s that starts with the same character. And the last is L, which is length of the substring corresponding to I to j. Now we always start the procedure call with BWT reverse and k value is 1. The I to j value is 1 to n being the length of the string which we have, and the L value is initialized with 0. We start the call by making this BWT call, and then the algorithm heavily relies on the get intervals functions. So if you can see, as soon as we enter the algorithm, we have the first function called to get intervals. Now, for any omega intervals of I to j, where omega is the substring of the string s, the get intervals of I to j returns the list of all the C omega, or basically the character omega's intervals, where C belongs to the alphabet set. We will come to understand this much better when we look at an example later. So assume now that we have a list generated. The get intervals returns a list of ranges. So assume we have the list ready with us right now. We iterate through this algorithm until the list is empty. So based on the condition, we calculate the value at each index of the BWT reverse array. This is a modified version of the complete algorithm. So this algorithm demonstrates only the applications of BWT reverse, whereas the complete algorithm computes partial SA reverse and the LCP reverse array as well. Now here is the algorithm for get intervals functions. A much simpler way to understand this procedure would be to search for the common character in the string S, or the character represented by the range passed to the get intervals function. Yep. So for example, let's consider if we are passing a range of 2 to 5 and we get the output as 2 to 3 and 8 to 9. How do we proceed with that is, once you receive a range of values to the get intervals functions, we see what is the character that it represents in a suffix array. So in a suffix array, whenever you have a group of index values or a range of index values, it represents a particular suffix or a group of suffixes that starts with the same character. And once you have that character, we look for that character in the string and we check one character before that. So the first character before that would be the character we are looking for, and combining both of these, we now have a new interval. We can understand this much better when we dive into the example later. So let's consider an example of string S, which is C T AAT G dollar. If you see, we have the characters C, G, and dollar appearing just once, whereas the character A appears 4 times and T appears 3 times in the given example. I've calculated all of the suffixes of these. So once you have all of the suffixes calculated over here, we have the suffix 10, and the suffix array value is 10, 3, 6, 4, 7, 1, 9, 5, 2, 5, and 8. Yeah. And corresponding to all of this, let's say we have the suffix array index of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So at the first index over here, if we see, we have the dollar symbol, and at the index from 2 to 5, we have A, and then at the sixth index, we have C, and 7 we have G. The index range from 8 to 10 corresponds to the character T, which means that all of the suffixes start with the character T over here, which is over here. Yeah. So moving on to this, yeah. At the start of the get interval function, when we pass it of range of 1 to 10, it returns as a list, which is 1 to 1, 2 to 5, 6 to 6, 7 to 7, and 8 to 10. Now 1 to 1 corresponds to the dollar symbol, and 2 to 5 corresponds to the A character, 6 to 6 is for the C character, similarly 7 to 7 is for G character, and 8 to 10 corresponds to the T character. Now, how do we proceed with this? We only require the suffix array for the entire string, and the suffix array is already computed. We can always generate the suffix array, and we have the string length of 10. This is our given string. And this is what we want to achieve, the BWT reverse array. BWT reverse array is achieved by computing all of the values from left to right order. Now, let's take the first example or start with the list of 1 to 1. So when we call the BWT reverse function and we iterate on the list of 1 to 1, the lower left bound and the right bound is 1. Left bound and right bound, since they are equal, we calculate the position value. So the if condition which we had in our algorithm relies on two sub conditions, which is if LB equals to RB, or the SA of LB plus L plus 1 equals to the SA of RB plus L plus 1, and we take the characters at both of these values. Since LB equals to RB in this case, we calculate the position directly. So position would be SA of LB. LB in this case is 1, and L in this case is 0, because we have initialized L with 0 over here, and then plus 1. So position is 10, which is greater than our position is 11, which is greater than our index, the length of the string 10. So we update the position to 11 minus 10, which is 1. So at the first position in our string, whatever the character we have, that is C in this particular case, will be the character, first character in our BWT reverse array as well. We always iterate in this loop to fill the BWT reverse array. This loop ranges from k, this first index would be k, to k plus RB minus LB. There are certain scenarios or cases, and even in our example, we see that some characters are repeated. Let's say the character A comes 4 times and the character T comes 3 times. So instead of always iterating through them again and always computing them again, if there are exact same elements that come in a continuous order in our BWT reverse array, we just compute them once and populate the BWT reverse array immediately. So coming to the example, or for the list 2 to 5, now we have the k value as 2 and L value as 0. After each successful population of the BWT reverse array, we increment the k value. So k value here is 2, L value is 0. And we see LB is not equals to RB, so we check for the other if condition. SA of LB plus L plus 1, which is 4, and for RB it is 8. We check for the string or the character value at these particular two positions in the string at 4 and 8, which is A and T. Now, since they are not equal, we do not go into the if condition and we go to the else condition directly. So anytime we go into this else particular else condition, we make a recursive call to BWT reverse array. We pass the k value and then the new index range, which is 2 to 5, and always increment the L value to 1. Again, we call the get intervals function on 2 to 5. Now this gives an output of 2 to 3 and 8 to 9. I'll explain in detail how the get interval functions takes a particular range and then gives a list of ranges as the output for this particular case. And going forward, we'll again be using the get interval functions quite a lot, but that time you'll have a much better understanding how it works, and I'll not be explaining them in much details. So as of now, the get interval functions for the input of 2 to 5 returns an output of 2 to 3 and 8 to 9. Going back to this particular slide, yeah. So the get interval functions received the input of 2 to 5. So if we check in the suffix array of 2 to 5, we have these particular elements 3, 6, 4, and 7. Now all of them correspond to the character A, which basically means that all of the suffixes start with character A. So if we check for position number 3, 6, 4 and 7 over here, we see that all of the characters are A. Now what we need to do is consider the character just before that. So at position number 3 where we have A, consider the element just before that. So in that case we have this particular character of T. So we have one group of TA over here. Now if we do similarly for the index 4, we have A over here. We check just the previous element of it, and now we have another group of AA over here. Similarly, at position number 6, if we go for it, we have another group of TA, and position number of 7, we have another group of AA. So overall, we received two new groups, which is TA and AA. Okay, so we sort these groups in a lexicographical order. So we have AA first and then TA. Now what we need to do is we need to see which of these suffixes starts with AA and TA. So if we can see over here, there are two suffixes that starts with AA, and there are two suffixes that starts with TA. Sorry. So we have AA over here, we have AA over here, we have TA and TA over here. Now, what are the index values of these particular positions? So this AA comes at index 2, this comes at index number 3, this comes at index number 8, this comes at index number 9. So that is the reason the get intervals of 2 to 5 returned an output of 2 to 3 and an output of 8 to 9. So now we have two new sub lists, and if we go over here, we saw that this was the output given by 2 to 5. Now we iterate on these particular lists. So 2 to 5, we got these two new outputs, and now we are iterating on the list 2 to 3, where k is 2 and l is 1. Again, same way we calculated the suffix array values and then the element at these particular indexes. So we have the same elements here now. Now, if both of the elements are equal, our if condition passes, and then we go in the if condition, we calculate the position value. Position value is 5 in this case, and the left bound and right bound is not equal. So we just take the character which appears at the fifth index in the string, which is T in this case. And again, now we populate the value T in our BWT reverse array. So we populate it from a range of 2 to k, like it's basically k to k plus rb minus lb, which is 3. So at the BWT reverse array, at the index number 2 and 3, we populate the character t and increment the k value. Similarly, we do it for the list of 8 to 9, where k is 4, l is 1, lb is not equals to rb. In the exact same way, we populate the BWT reverse array at position number 4 and 5, and this time we get the character a. So up until position number 5, we have populated our BWT reverse array. Now we are coming out of this particular loop or this particular recursive call of list 8 to 9, and we again go back to the position where L was 0. And the next list we have is 6 comma 6. So at this particular position 6 comma 6, we have k is 6, L is 0. The left bound is equals to the right bound, hence we directly go into the if condition. Now the position at this particular case, SA of lower left bound plus L plus 1 is 2, which is less than 10, and we check for the character at the index number 2 in our string, which is T. So we directly populate the BWT reverse array at position number 6 as T. In the exact same way, we do it for position number 7. So we have the k value 7, L value 0, and we compute and we get the BWT reverse at position number 7 as $. Coming to the final element of this or the final list, we have 8 to 10, where k value is 8, L value is 0. So now since LB is not equals to RB, we compute these values. SA of LB plus L plus 1, which is 3, and SA of 3 is A, SA of 9 is G, which are not equal. Hence we go to else condition and we make a recursive call to the BWT reverse procedure. K value is 8, index values are 8 to 10, and L value is incremented to 1 in this case. So now the get intervals again receive a new interval which is 8 to 10, and this time we have the common prefix of t. Next character which we have after this is a comma, it should be c over here. Yeah, so the characters which we have now at this time just before these indexes is a and c. So this is the group we have at and ct. Since L value was 1, we know that means they have only one character in common, or basically one prefix in common, which is TT, one suffix. Yeah. So AT appears at index 4 and 5 in our suffix array, and CT appears at index number 6 in our suffix array. So first we'll compute for AT, which is at index number 4 to 5. So when we have the list of 4 to 5, K as 8, L as 1, again the left bound is not equal to the right bound. SA of 4 plus 1 plus 1, which gives us 6, and SA of 5 plus 1 plus 1, which gives us 9, again gives us the same output of A and G, which are not equal. Hence, we again make a recursive call to BWT reverse by passing 4 and 5, and L value increments to 2 this time. L value incremented to 2 means there are two elements which are similar at both of these indexes, and we again need to take one element on the left side or one element before these indexes and check where they appear in the suffix arrays or the suffixes. At whichever position they appear, we consider the suffix array index of those values. So get intervals of 4 to 5 will give us the output of AAT, which is the range of 2 to 3. So our left bound is 2, right bound is 3. List 2 to 3 and K is equals to 8, L is equals to 2. We again compute the SA, and again we get S of 6 and S of 9, which is A and G, which is not equal. So again we make a recursive call of BWT reverse, and this time incrementing the L value to 3. So the get intervals for 2 comma 3 will return TAAT as the value, and the indexes for this will be 8 to 9. If you notice, every time we make the get intervals call, the character increases in the length. So we have TAAT now. Earlier we had AAT, and just before this that we had AT, and we started with T before that. Yeah, now we compute for list of 8 to 9, where we have the L value of 3, and we again get S of 6 and S of 9, which is A and G, which are not equal. We make the BWT reverse call again, this time with the L value of 4. So earlier we received TAAT, and now we received AT8, AT, and CTAAT. Now AT comes in our suffixes at position number 4, so suffix array index of 4. CTAT comes at position number 6 in our suffix array. So again we compute for 4 4 and 6 6. Now if we compute for list of 4 4 where L is 4, we see that the left bound is equals to the right bound. So we go into the if condition, we calculate the POS value of it, and that is position value is 9. So we check for the ninth character in our string, which is G. Hence the BWT reverse at position number 8 will be G. When we increment the K value to 9, now we compute for list of 6 to 6 in the exact same way, and we see that the BWT reverse array at position number 9 is A. We increment the K value to 10, which is the last element in our BWT reverse array. Coming out of all of these recursive calls, we again go back to the main final call, where we have the list value of 6 comma 6, L value as 1, and K is 10. 6 comma 6 satisfies our condition of LB equals to RB. We calculate the position, which we get 3, which is less than 10, and the third element in our string is A. Hence the BWT reverse array at the 10th position is A, and once we are done with all this, our list becomes empty, so we run out of the while loop as well. So after all of these computations, our BWT array is finally complete, and the computation of BWT array, as we already saw, happened in a left to right fashion. We computed BWT reverse of 1, 2, 3, and so on. So the two major components of this algorithm are if each occurrence of the character C omega character in the set of the substring of the string S is followed by the same character A. In particular, this is true whenever LB equals to RB, as we already saw so many times in our iterations. Then each occurrences of omega reverse of C is preceded by A in S reverse. Thus, BWT reverse of Q equals to A for every Q in this particular range. So what this tries to say is the same for loop which we ran at the end of every iteration to populate the similar characters is bounded, the Q in that is bounded by K as the lower bound and K plus RB minus LB as the upper bound. And the second important component of this is if the characters are not same. So the first case was if the characters are same. Second case is if the characters, not all the characters in the BWT reverse of this particular range are same. Then the algorithm recursively determines the lexicographic order of the suffixes. So we saw that if we do not match the if condition, we go into a recursive call in the else condition, and we again keep on lexicographically sorting the orders, but that is done by the get intervals function. So after all of the computation, we receive the BWT of the reverse string, which is this $GAA, which is exactly what we got after all of the iterations. So this here is the BWT of the reverse string, and the algorithm and the main component which we were focusing on for all this time was this one. So if LB equals to RB or this condition. So there are two important conditions to note over here. Now this is the recursion tree for it. As we know, we started with the root node that had all of the elements, and then we had a dollar sign which was at the starting index, I guess 1 to 1, and then we had 2 to 5 index. So this was index 1 to 1, this was 2 to 5. 2 to 5 was split into 2 to 3 and 8 to 9, and then we had 6 to 6, 7 to 7 index, and then we had 8 to 10, which had a lot of recursive calls in that, which we can see over here in the recursion tree. And finally we received 8t AAT and CT AAT in that, and the 6,6 which was remaining at the last was CT. Corresponding to all of these, we receive the BWT values over here. So this was the BWT reverse array values for the given string. Now, to compute the worst case time complexity for this, we need to understand that the overall number of intervals written by the calls to this procedure get intervals is bounded by 2n minus 1. Now, how is it bounded by 2n minus 1? The calls only happen for internal nodes is what we need to remember. In the recursion tree which we saw earlier, if we notice all of the calls which were made to the get interval functions or the BWT reverse function were made from the internal nodes only. So considering this as one internal node, we made one BWT recursive call over here. Considering again this as an internal node, we made a recursive call. We made a recursive call here as well, and we made one here as well. We made one call here as well. So we make only recursive call of BWT reverse functions when it is an internal node. Now, if L is a concatenated list of all the intervals that we receive from the getIntervals function, for each element there can only be two scenarios. So at least one entry of BWT reverse is filled by it, or there is a recursive call. So either we populate the BWT array going into the if condition, else we make a recursive call to the BWT reverse. So L will have at most 2n minus 1 elements, because if the BWT reverse array has n entries, we have n cases over there, n chances over there, and there can at most be n minus 1 recursive calls to the procedure BWT reverse array. Since that can be the maximum number of internal nodes a given tree can have. So that is the maximum number of recursive calls, which is n minus 1 that can happen. Hence, we can say that the getIntervals function or the entire procedure is bounded by n plus n minus 1, which is 2n minus 1. Yeah. So, uh, now that we have understood that getIntervals is bounded by 2n minus 1, we can understand that there are as many recursive calls to the procedure this BWT reverse as there are internal nodes, which we already saw in the recursion tree as well. Now, because the suffix tree has n leaves, and each internal node in this suffix tree is branching, the number of internal nodes can at most be n minus 1. Since this is not a binary tree or any other tree, we can have at most internal nodes n minus 1. So it is a consequence of this analysis using the recursion tree and using the properties of get internal functions and BWT and the reverse of the string. We can say that the time taken by all the procedure calls to the get intervals is O of n log sigma. And in a very generalized way, the get interval functions for k elements that returns a k element list takes k log sigma time. And since we have n as the string's length, this time complexity becomes O of n log sigma. Now, this entire algorithm of computing BWT of a reverse string without actually reversing a string has lots of practical usage. So some of the uses for this bidirectional search, so BWT of a normal string or a string in a simple order can easily be computed, and now we are also able to compute the BWT of a reverse string. Hence it is a bidirectional search, and it has lot of uses, especially in RNA structure detection and genome sequence alignment, efficient genes search in large genomic databases, RNA targeted drug delivery, evolutionary studies of RNA. So this algorithm's ability to provide like bidirectional search showcases its versatility and efficiency in biological sequence analysis and genome research, making it valuable for detecting structural patterns and accelerating computational biology researches. So I hope you understood the algorithm, and if there are any doubts or any comments, feel free to reach out to me. Yeah. The reference was for this entire presentation was taken from a book on bioinformatics algorithms by Anno Olebush, and the ISBN of the book is noted. You can give it a read. It's very nice and explained in a much detailed way over there. So yeah, that's about it. Thank you so very much.